Calculating the area of circular or curved regions is often difficult using standard rectangular coordinates. By transforming our perspective into polar coordinates, we can simplify complex boundaries into manageable integrals. Today, we will explore the derivation and application of the polar area formula. In the Cartesian system, we use a grid of squares. However, for shapes with radial symmetry, it is more natural to define points by their distance from the origin, r, and their angle from the positive x-axis, theta. To move between these worlds, we use these fundamental transformation equations. These relate the horizontal and vertical components to the radius and angle, forming the basis for our change of variables in calculus. The building block of polar area is the sector of a circle. Unlike rectangular area, which uses of width times height, a polar sector's area is proportional to the square of the radius and the infinitesimal change in the angle. By summing up an infinite number of these tiny sectors between two angles, alpha and beta, we arrive at the definite integral for polar area. This formula allows us to calculate the space enclosed by any continuous polar function. Think of dA as our area element. As the change in theta becomes infinitely small, the wedge behaves like a triangle with a height of r and a base of r times d theta, leading to our 1/2 r² expression. Choosing the correct limits is vital. We always integrate in the direction of increasing theta, usually starting from the positive x-axis and sweeping counterclockwise to capture the desired region of the graph. Let's verify our formula with a simple circle of radius 3. In polar form, the equation is just r equals 3. We expect the area to be 9 pi. Let's set up the integral to see if it matches. We substitute r equals 3 into our formula. Squaring 3 gives 9, and half of that is 4.5. Integrating 4.5 with respect to theta over the full circle gives us exactly 9 pi, confirming our method works. Now consider a more complex shape, the cardioid, defined by r equals 1 plus cosine theta. This shape is not easily calculated in rectangular coordinates, but polar integration handles it elegantly. To find the total area, we square the function. This gives us 3 terms to integrate. Note that the squared cosine term will require a power reduction identity to solve, a common step in polar area problems. We can simplify our work by using symmetry. Since the cardioid is identical above and below the x-axis, we can integrate from 0 to pi and multiply the result by 2. This often makes the evaluation much cleaner. After performing the integration and applying the limits, we find the area of this cardioid is 3 pi over 2. This demonstrates the power of polar coordinates for shapes defined by radial functions. Before integrating, you must find where the curves intersect to determine your limits. Set the two equations equal to each other and solve for theta. Always verify these points on the graph to ensure they make sense. To summarize, always start with the standard polar area formula. Identify your limits of integration by looking at the graph or solving for intersections, and remember to use trigonometric identities to simplify your integration steps. Try this. How would you set up the integral for just one petal of the 4-petaled rose r equals sine of 2 theta? Think about the limits needed to start and end at the origin. The answer involves integrating from 0 to pi over 2. Coordinate transformation is a vital tool in calculus that turns difficult problems into simple ones. With these techniques, you can now calculate the area of virtually any polar shape. Thank you for watching. Generated by Vision Solve AI.